hello everyone. So in this particular video we are going to discuss the hydrostatic forces, buoyancy and flotation in fluid mechanics, and we are going to do all the previous year questions that has come into GATE exam. So let's start with the very first question of 1 marks which came in GATE 2022. The question is, a body floating in a liquid in a stable state of equilibrium, if its center of gravity is below its center of buoyancy, metacenter lies below its center of gravity, metacenter coincides with its center of gravity, and metacenter lies above its center of gravity. So see, we have to understand the concept of metacenter whenever there is a term of floating body. Whenever there is floating body, there is something called metacenter that exists. So what is metacenter? In this particular question, we should be having the metacenter above the center of gravity. So how it works? Let's say I have this body and which is in liquid. So if I see, let's say the gravity is here somewhere which acts downward, buoyancy is here somewhere acting upward. Okay, if I talk about the metacenter in this case, I have said that in floating bodies metacenter should be above the gravity. Okay, that means the distance gm should be positive. So if I say the body is trying to float but there will be tilt sometimes, and now if I see the center of gravity is somewhere here of the body, it works downward. Okay, center of gravity works somewhat like this, and the buoyant force B, this buoyant force will also act at the center. So the buoyant force, let's say, meets with the center somewhere here. Okay, let's say it comes in B dash, and this buoyant force meets the center somewhere here. This particular point we call as metacentric point. So this is metacenter of the body. When the metacenter is above the center of gravity, that means, see, now the buoyant force is acting at this particular point. So see, this gravity force is trying to tilt the object, trying to bring the object downwards, but the metacenter or the buoyancy force is trying to make it upward again. So it is trying to do like this, and the metacenter is again trying to lift it like that. So that means the body is stable and is floating, it will never tilt down. So this is the case. And in other hand, if we see that body is somewhat like this, so if in some case, let's say center of gravity of the body is somewhere here, it is working like this. Let's make it little bit clear. Let's say this is the center of gravity of the body, and it is somewhere here. This is working like this. Buoyancy was somewhere here. If the buoyancy comes till here, B dash, the point where it meets the center line is GM. Now the buoyancy is working like this. See, now center of gravity is trying to tilt the body like this, and buoyancy is going upward, and it is also helping the body to tilt like this. That means when the metacenter is below the center of gravity, that means it is unstable. So for the particular stable case, we should always have metacenter greater than or above the center of gravity, or in other case the distance is gm, right? So this gm distance is positive. If this gm distance is positive, gm is nothing but m minus g. Okay, so this comes as gm. So if this is positive, that means the body is stable. So here Meta center lies below its center of gravity, it will not work. Meta center coincides with center of gravity. Neutral state. Neutral state we don't want. We want a stable state. So meta center will lie above the center of gravity. So let's do the next question. For a body completely submerged in a fluid, the center of gravity G and the center of buoyancy O are known. The body is considered to be in stable equilibrium if O does not coincide with the center of mass of the displaced fluid, G coincides with the center of mass of the displaced fluid, O lies below G, O lies above G. So we have the four options, and now we are talking about the fully submerged body, completely submerged. So we have discussed the case of floating body. Now we are going to discuss the case of fully submerged body. So in fully submerged body, let's say this particular is the body. They are saying that the center of gravity as G, center of gravity as G, it always works downward, okay, and the center of buoyancy, let's say O, which is the force of fluid that is supporting this body. So buoyant force, let's say FB, and it is working at O. Now the body is considered to be in stable equilibrium when, let's say, the body gets tilted like this. If we want a stable equilibrium, so for stable equilibrium, I want the effect of gravity to be cancelled out with the buoyant force. So if the gravity is somewhere here, let's say downward, okay, this is the gravity force. This gravity is trying to tilt the body like this. So the buoyancy should act upward. So the gravity is trying to tilt like this, and then buoyancy is trying to make it stable. This is FB. In other hand, if the buoyant force or center of buoyancy lies below the center of gravity, let's say this is the center of gravity and this is the center of buoyancy, FB works like this. See here, it is making a couple, and the couple is trying to tilt the body like this. So the body is not in stable condition here. That means for the fully stable condition, we should be having O lies above G. So option D is correct for this as well. Now we have question number 3. The force F required at equilibrium on the semi-cylindrical gate shown below is, see, we have this particular diagram. 2 meters of water is covered by this gate. It is connected by a hinge. It is a cylindrical gate, that means a semi-cylindrical gate. That means if we see the 3D view, it can be somewhat like this. It is going like this, okay. So this is the gate which is supporting the water. It is not allowing the water to come out. Now I want the force F required at the equilibrium on the semi-cylinder gate shown below. So it is the case of submerged curved bodies, static force on the curved bodies. The resultant force for the submerged body or for the curved submerged bodies, okay, it is curved body submerged in water. I want the hydrostatic force in this condition. So the resultant hydrostatic force is nothing but under root of your vertical hydrostatic force square plus your horizontal hydrostatic force square. So it is the summation of vertical and horizontal. Now what is horizontal? What is horizontal force? So horizontal force is nothing but, see, the projection, this is the horizontal force, okay. Horizontal force is nothing but the pressure, okay, till this point, how much pressure this body is is able to withstand. So pressure per for a particular area. What is the area? It is till the length. Length we don't know here in this case, so I can take it as unit length, right? So for unit length I want to know the horizontal force. So horizontal force acts, it is the pressure, right? So the pressure will be acting from the top. This gate is from the top, let's say till 2 meter height. Okay, so from the top till 2 meter height I have the pressure. See, initially height is 0, so pressure is 0 at particular point F. Okay, so at point F the pressure, final pressure is rho gh. So rho gh, h is the height, that is 2 meters. Okay, so it will come something like this. This is the maximum pressure, and above this the pressure will be reduced linearly. So the pressure diagram is like this. I want to calculate this particular pressure. So this is the pressure diagram. I want to calculate the force now. So the resultant force will be acting on, because it is triangular pressure diagram, it will act at 2/3 from the bottom. This pressure will act at 1/3 from the bottom. So let's say this is pressure, horizontal pressure, and it will act as 1/3 from the bottom. So total is 2 meters, so it will be 2/3, right? 1/3 means 2/3 meters of length it will be acting. I can calculate this pressure. This pressure is nothing but the area of this triangular loading. So the pressure pH is equal to 1/2. Total height is 2 meters and the width is rho, width is gamma WH, that means rho g, and height 2 meters. That means 1/2 into 2 is the width into rho, that means it is having 1000 into g 9.81 into height is 2 meters. So it comes something, if I change it in kilonewton, it will be to cancel, it is something 19.62 kilonewton. This is the loading. Okay, so it came horizontal. This is nothing but force in the horizontal direction. If I get this is the case of horizontal loading. See, this was the pressure. I am giving it, I am naming it as pressure. This is nothing but the horizontal force. That means what I am doing, see, rho gh is nothing but the pressure. If I am multiplying it with, this is kilonewton per meter square. Okay, and this is kilonewton, and I am multiplying it with meter, so it is giving me kilonewton per meter, and per unit I am taking, I don't know the width, right? So per unit, that means it became kilonewton per unit width, so I can take it as force directly. Now what is vertical force? Vertical loading is nothing but the weight of liquid supported by the projected area. Okay, so the weight of liquid supported by this particular body. So from here, see how much liquid, how much water is supported in this. Can we say, see, weight of the water above the body, this is the center. Below this the water is not supported. Even water is supporting this body, we are not going to take that. But above this the water is somewhere till here, if I can say maximum, this much water is getting supported by this particular body. So if I calculate the volume of this, so that only will give you the weight, that only will give you the vertical loading. So now this how can I say how much volume it will be there? Still here, like this. Okay, till full, and it will go somewhat like this. So this much fluid I want to calculate how much volume of fluid is there. Particular vertical force is nothing but the weight supported by the liquid, weight supported by the object of the liquid, weight of the liquid supported by the object. So let's say this is the weight of the liquid, that is nothing but Fv, and it acts at the CG of the body. So it is semicircle, right? Semicircle. First I will calculate the force. Force is nothing but weight supported by the liquid. So how much weight it is supporting? The area is, if I say Fv, right? So Fv is area. How much area is this much? Area, this is pi r square upon 2, pi r square upon 2. This much area. How much water it is supporting? Till length, particular length will be there. In this case we are taking it as unit length. So pi r square into L. What is this? This is volume. Area into length becomes volume into, I have to do rho g, rho and g. Why? Volume into density gives the mass, right? And mass into gravity will give you weight. So I want the weight. So this is nothing but Fv is pi r square. Put the values. We have pi by 2 into radius is 1 square into length is, I am taking unit, I don't need to consider that. Let's say 1, this also, into g 1000 into g 9.81. Okay, so the vertical force I got, that is around 15.41 kilo Newton. This is the vertical force. Now the case is, where should it act? So it will act at the CG. So the CG of it will come of semicircle comes somewhere around this, and that the distance, this particular distance is x bar. X bar is nothing but equal to 4 r upon 3 pi. This is nothing but 4r upon 3 pi. Just need to remember this, or you can calculate it as well. I'm just putting this like directly. So I have this Fv value as 15.41, will act at 4r, x bar will act at 4 into 1 upon 3 pi. So this is the force, right? So this is the vertical force acting here. Okay, I will remove everything. Now I will show only the forces here. Let's say, see, this is the clear picture. Now I will just show the vertical force will act somewhere here, right? And the horizontal force is acting, this is the acting point, and horizontal force is acting somewhere here. Okay, this is the horizontal force. So I have to take the moment to get the resultant force on the hinge to be semi-cylinder. Okay, it wants to be stable. So stable, so the resultant on the hinge I can calculate as, this is Fv and this is Fh. Fh into, what is this distance? This is 1 minus 2 by 3. So this is Fh into 1 minus 2 by 3. Okay, this is like this, in this direction. That means anti-clockwise, and Fv is giving from to the hinge clockwise. So let's say Fv negative, anti-clockwise positive, and clockwise negative. Fv is at the distance 4 upon 3 pi, right? 4 upon 3 pi. So Fv into 4 upon 3 pi. And what extra force they are asking, right? So the force F required at equilibrium on the semi-cylindrical gauge shown below. Okay, the force is given like this here, F. I want to calculate the force F here. So the force F is giving the moment somewhat like this. That means clockwise. That means I will take it also as negative. Okay, this is positive. I will take it also as negative F into 1 equal to 0. Let's calculate from here. I get Fh. I will put Fh values. That comes as FH was 19.62 of 1 minus 2 by 3, that means 1 by 3, and minus FV is 15.41 into 4 upon 3 pi is nothing but equal to F. So let's calculate the values. So it comes as 6.54 minus 6.54 equal to F. So the value of F is 0. So we don't need any extra force here to make it in equilibrium. The gate is already in equilibrium. So this is the conclusion for this particular question, question number 3. Okay, so the answer is B, 0 kilonewton. Okay, so let's work with the question number 4. In an iceberg, 15% of the volume projects above the sea surface. If the specific weight of sea water is 10.5 kilonewton per meter cube, the specific weight of iceberg in kilonewton per meter cube is. So see, they are saying there is an iceberg and which is 15% of that is above the sea surface. That means 85% of the iceberg is in the sea surface. So if I draw, let's say for our imagination, this is 15% of the iceberg, and let's say this is the sea surface, and that means 85% of the iceberg is below the sea surface. So they are saying, so it is a floating body, right? Because some part of it is above the sea surface, right? So for the floating bodies, we know that weight of the body is supported by the weight of fluid displaced, right? So weight of body is equal to weight of fluid displaced. This is also a important concept in case of floating bodies. So this we should know. The weight of body is nothing but how much fluid the body is displacing. So in this case, we have the weight of body. How can I calculate? Rho of iceberg, let's say I for iceberg, rho G, and V मतलब volume of iceberg. Okay, so rho G is nothing but the unit weight, okay, into the volume. It will give you the weight of the body is equal to weight of fluid displaced. How will I calculate the weight of fluid displaced? So the density of your seawater, let's say seawater is SW, into the specific gravity. See, if it is water specific gravity is 1, we don't need to include that in this question, in this particular equation. But if there is any other liquid other than water, we have to specify its specific gravity as well. Okay, specific gravity of seawater, then G, and then volume of iceberg. Volume of water is nothing but the volume of iceberg that was replaced. So volume of iceberg. That means I got here rho G is nothing but unit weight. So gamma of iceberg is nothing but, see, volume of iceberg both here in both the equations are in both the sides it is equal. I will cancel it out. So rho G, and this is rho, and this is gamma of seawater into what is the specific gravity given in the question? Specific gravity, okay, specific weight they have given. Specific weight of seawater is 10.5. So I can simply put the specific weight here of seawater directly, 10.5. This is nothing but specific weight 10.5 kilonewton per meter cube, and a specific gravity of seawater, if they must be given it, It is not given in this particular question, but we should know the specific gravity of seawater. If it is not given, we should remember the specific gravity of seawater is nothing but 0.85. So I will put 0.85. So it comes as specific weight of iceberg is nothing but 8.925 kilonewton per meter cube. This is the particular answer, and they have asked the specific weight of iceberg, that is nothing but 8.92. So closest answer is 8.93. Fourth question is also done. We have question number 5. The center of pressure of a liquid on a plane surface immersed vertically in a static body of liquid always lies below the centroid of the surface area, because in liquids the pressure acting is same in all directions. There is no shear stress in liquids. At rest, the liquid pressure is constant over depth. The liquid pressure increases linearly with depth. So these are the four options, and the question says somewhat like this: that if body is vertically submerged, okay, that is immersed vertically. Submerged means fully submerged body is there. So let's say there is a rectangular plate. Okay, I am seeing it with the side view. So if this is the sea surface, on this is the water surface, and the body, this our body, I am seeing the side view, is vertically submerged. Okay, so if the body is vertically submerged, see, CG will be somewhere like here. I will put the CG here. They are saying the center of pressure lies below G. Okay, so this is center of pressure. Okay, so they are saying it is always below G. See, if I say, see the pressure diagram, previous questions also we have seen the pressure diagram. Pressure diagram is nothing but it starts from this particular end to this particular end. The how much pressure will be here, see, somewhat like this, depending on the height, rho, G and H. Okay, so till here, here the height is somewhat less, here the height is somewhat more, so the pressure will become more. So I get the pressure diagram somewhat like this. Now this pressure diagrams center of gravity will give you the point where center of pressure works. Okay, so this hydrostatic force is acting on this particular point at particular place. Now they are saying the center of pressure is always lie below the center of gravity. That is because center of pressure increases with height. So here, when height starts increasing more than G, the value starts increasing. If the value starts increasing, it will definitely lie below G, not the above G, because above G the values are less. Below G the values are more. So it will act here below. So the liquid pressure increases linearly with depth. So this is the final answer. D of question 5. It came in GATE 1998. Now we have question number 6. In which one of the following arrangement would the vertical force on the cylinder due to water be maximum? See, vertical force due to water be maximum. Okay, these are the four conditions. So vertical force is nothing but the weight of liquid supported, right? So weight of liquid supported, let's say this is the, see, this much liquid is supported here. Okay, above this surface this much liquid is there. Now in B also, if I see same amount but in opposite direction, this same liquid is supported. Okay, in C as well, the weight of liquid, even though it is down here, but here water is supporting the body, not the body supporting water. In this particular area the body is supporting water. So till now all the three places I am seeing the water is supported, same amount of water is supported, the same amount of vertical force is acting. Okay, question the option D is having, see here also the vertical, this much water is supported, and here also this much water is supported, almost double. So the total force will be this plus this. So this is the maximum force. So D is the answer, directly we can say. Just to need to examine this. Now I have another question, question number 7. One of the following statements is true with regards to bodies that float or are submerged in liquids. Okay, so it is in regarding to floating bodies or submerged bodies. For a body wholly submerged in a liquid, the stability is ensured if the center of buoyancy is below the center of gravity of body. For the body floating in liquid, the stability ensures if the center of buoyancy is below the center of gravity of the body. For the body floating in a liquid, the stability is ensured if the center of buoyancy is below the center of gravity. For the body floating in a liquid, the stability is ensured if the center of buoyancy is below the center of gravity and the meta center above both the center of gravity and buoyancy. So clearly I can say the option D is correct. Why? Because for a floating body, till now we have discussed so many things about floating bodies and submerged bodies. So for a floating bodies in a liquid, the stability ensured, see, when will the body will be stable? When the center of buoyancy is below center of gravity and meta center is above centers of gravity and buoyancy. This case we have seen in very first question, when meta center above center of gravity and buoyancy will definitely be below the center of gravity. So this is the case that is correct. So why A, B and C are not correct? Let's say A, for a body wholly submerged in a liquid, fully submerged body, the stability ensures if the center of buoyancy is below the center of gravity. So we have just now we have seen in previous question, one of the previous question, where I have shown if center of buoyancy is below the center of gravity, it is unstable condition. So stable condition is when the center of buoyancy is above center of gravity. So A is definitely wrong. B is a body floating in liquid, the stability ensured if the center of buoyancy is below the center of gravity of the body. Then now they are asking for floating bodies, and floating bodies they just gave the condition of buoyancy, not the condition of meta center. So center of buoyancy is below the center of gravity, that is always the case in floating body. But the main case is if we have to check whether the meta center is getting upper than the center of gravity. If meta center is above the center of gravity, then only body will be stable, not the condition of buoyancy. So this is also wrong. For a body floating in a liquid, the stability is ensured if the center of buoyancy is below the center of gravity. Again, the same option C, again they have given the same thing. Body floating in a liquid, the stability ensured if the center of buoyancy is below the center of gravity. Not fully, so this is not correct. Okay, let's see question number 8. The force per unit width on the rectangular door submerged in a liquid of density rho. Figure shown below is, this is the figure. Force per unit width on the rectangular door, this is a rectangular door, submerged in a liquid of density rho. I have to calculate the force. So the force is nothing but it will be acting somewhere. See, the CG is here. The force of the body will be acting somewhere here. F, this, let's say hydrostatic force, I am saying F. So this hydrostatic force is nothing but rho G H bar into A. This is the formula for hydrostatic force. Now if I put the values, I have rho is density, it is water, right? submerged in a liquid of density rho. I don't know the liquid is water or not. They have given the liquid's density as rho. So so rho we know, g we know, area also I can calculate. Only thing is h bar. H bar is what? The effective vertical depth of CG. H bar is nothing but, see, this is not the h bar. This is the height of the, this is the center of gravity, height of center of gravity of body, but vertically what is the height? That is h bar. That I need to calculate. So the vertical height will be equal to, how can I say the vertical height? Let's say this is 1 meter, so half will be 0.5 meters. 0.5 and 0.5 sine 45. Okay, sine 45 will give h bar upon 0.5. So 0.5 into sine 45 will give you the h bar value. So h bar is nothing but just simple trigonometry. H bar is 0.5 into sine 45. Okay, now I will put force is nothing but rho g into 0.5 into sine 45 value is 1 upon root 2, and area. Let's say area I have not given. Let's say unit width and unit length. I got the value as 2 root 2, right? This is 0.5 is nothing but 1 upon 2 rho g upon 2 root 2. So the value here is matching with option C. So the question number 8 is also done. Now last question of 1 number is a floating body with its center of gravity at G and center of buoyancy at B and meta center at M is stable. Till now at this point we definitely know that meta center should lie above center of gravity. Wherever there is this option, G lies below M, this is the correct option. So option D is correct. So till now we have discussed the 9 questions. All the 9 questions we have discussed of 1 mark. So next we are going to see the 2 marks questions. So the question number 10 here is, a sector gate is provided on a spillway as shown in the figure. Assuming G as 10 meter per second square, the resultant force per meter length expressed in kilonewton per meter on the gate will be. So this particular question is the question of curved surface. So there is the concept of curved surface. What will be the hydrostatic force on curved surface? Okay, so for any curved surface, as we know, the normal hydrostatic force when the surface is plane, there is a plane, so the force is rho g h bar into A. A is the projected area and h bar is the height of the centroid of the body. If let's say if it is a rectangle body, this is the centroid. So height of the centroid from the free surface. So from the free surface, what is the height of centroid? That is nothing but the h bar. Now when the body is not a flat or plain body, if it is a curved body, then in that case we have three types of curved bodies. We have, one is, let's see, we have one body is something like this. Okay, something like this. There can be a body that can be something like this, or there can be a body that is something like this. Okay, so there can be three types of bodies here which can lie in a water surface. So let's say, see, if the body is of the first type, the water will be filled above this. Okay, if the body is of second type, water can be filled somewhat like this. The water is here somewhere. Okay, so see, for any curved body there are the force which is acting on the curved body can be divided into two forces. One is horizontal force and another one is vertical force. See, this is the curved body, and this particular small elemental area, if we take that, the force is somewhat in this direction, right? Perpendicular to the surface force will act. Now this force can have two components, one is vertical and another one is horizontal. So the horizontal component is Fh and the vertical component is F vertical. So this is the forces that we are going to calculate. Horizontal force is nothing but the projection. If we project the vertical area of this particular body somewhere here, so this projection, this projected area, we will get the horizontal force as rho g h bar into A. Here rho g is the density and the gravity, acceleration due to gravity, and h bar I have just now told is the height from the free surface. A is the projected area, projected area on vertical plane. So this horizontal force concept works for all these three types of bodies. It can the horizontal force will be same for this as well, this as well, this as well. With the same formula we can calculate, but for vertical forces it changes. Like, let's say for vertical forces, see, horizontal force is this and vertical force is nothing but, for this case, for the particular case number 1 and case number 2, the vertical force is nothing but the volume, the weight of the water that this particular object or this particular curved body is supporting. So the weight of the water this particular curved body is supporting is this much. If I get this much weight of the water, we can calculate it by this. Now the weight of the body acts downward, so this particular vertical force acts nothing but it acts in downward direction, Fv. So Fv is nothing but the weight that is supported by the object. So that will be rho. How will we calculate weight? So rho into g, density into acceleration due to gravity, and then density into volume will give mass, into acceleration due to gravity will give you the weight. So here I can say into volume. So volume of what? Volume of this particular area which is supported by the curved body. Now this particular concept acts for case number 1 and case number 2. In case number 2 as well, we can see that this much water is supported by the body. So the vertical force will act downward, Fv. Now for this type of cases, case number 3, here we see that in this case we don't see if there is any weight of water supported by this liquid, but here we particularly see how much water is displaced by the body. If the body was not there, how much water was there if body was not there, and now if body is there, how much water is displaced. So this is nothing but, see, this is the curved body and this much water this body has displaced. So how much water it has displaced. So, and see, displaced, that means the displaced water is acting on the body. The displaced water is making a force on the body. So this displaced water wants the body to go upward. So this displaced force will act upward. Okay, so here we will take rho gv, but the volume which was displaced. So here force volume will act the same, vertical force with the rho g, but with that v will be the body, the weight of water, the volume which the object displaced of the water. So like this we have three types of bodies generally we will see in the exam. See this type of question examiner will not give in GATE because it is very easy. 2 and 3 because concepts are working here, so the 2 and 3 is the major importance. So we see in the exam, see here if I see the question number 10, I again see that I have this convex body, right? This convex body, and this is the free surface. I can see that this convex body is displacing this much water, right? Now if I want to calculate the total force, here they are asking me the resultant force. So resultant force will nothing be but it will be, here I can say Fr is nothing but under root Fh square plus Fv square. And with that, if I am asking for the theta, right, angle of the resultant force, that will be under root that will be, theta is nothing but tan inverse of what? F of vertical divided by F of horizontal. Okay, so these two are the formulas from which we will get resultant force and the direction of the resultant. In this particular case we are given the sector gate. That means sector means it is a section of a circular area, right? So it is called a sector. Now this sector has a radius 5 and the angle of this particular sector is total 60, which is 30 half, right? So for the area of sector, I want, let's say first of all I will calculate the horizontal force. So the horizontal force for this particular case, see I have something, this sector with 5 meter radius and angle 30, right? And this will be somewhat like this. I have something. Now I want only this particular volume. Let's say first I am calculating horizontal force F of H, that will be nothing but rho g H bar into E area. Now see, H bar is what? Height is from the free surface is on the top of this gate, right? And so the H bar will be the half of the centroid of this sector. Centroid will act on the center, so that will act at what distance, that I have to calculate. So that will act at this particular distance. This particular distance is nothing but let's say it is A, right? So A is nothing but 5 into sine 30 degree. 5 into sine 30 degree. So that I get 5 into sine 30 is 1 by 2. So it is 2.5. So A is nothing but H bar. So this is H bar. Now I have to calculate the area. See, they have not given the length of the body in this direction, right? So I will take it, they have given per meter, so I will take per meter length. So area will be nothing but the height into length. Length is 1, so I will keep the height. Projected area, this area will project a rectangle there. This area will project a rectangle at this particular place, right? And this rectangle with the total height as, this is also A and this is also A because angle is same and 5 meter. So it will be total of 5 meter and with 1 as width, right? So I have, now I can calculate horizontal force as rho. They have asked me to take rho as 1000 into G as 10 into H bar is 2.5 and area is 5. So I get the force as, so I get 125,000 Newton per meter, right? And this I get 125 kilonewton per meter, but this is horizontal force. I want to calculate now vertical force. So for the vertical force, I have the formula rho g and v. Rho g is 1000 into 10. Now the volume displaced. Volume displaced is nothing but this particular area, this much area into unit length. Okay, so this much area, how can I calculate this area? So if I know the area of the sector minus area of this triangle minus area of this whole triangle, I will get this particular area. So area of sector we can calculate is nothing but area can be theta upon 360. How much angle of the sector? Divided by 360 into pi r square. This will give you the area of the sector. So here we have theta as 60 degree divided by 360 into pi, and radius is 5 square. So we get 13.083 meter square. This is the total area. Now I have to minus the area of the triangle. Triangle area is nothing but 1 by 2 into length into width, right? The perpendicular area. So perpendicular, this particular perpendicular, this one, I can get it by cos 30. So this is nothing but 5 cos 30. So into 5 cos 30 into height, total height is 5 meter of the triangle. So I get this is 10.825. So I get the resultant area as 13.083 minus 10.825. That gives us 2.257 meter square. So this is the resultant area that got displaced. I will put that here, 2.257. So this total is nothing but 22,576.8 Newton per meter. So this is 22.576 kilonewton per meter. Now I have the horizontal force, I have the vertical force. I can get the resultant, that is under root fv square plus fr square fh square, and that is nothing but 22.576 square plus 125 square. So it gives me 127.02 kilonewton per meter. This is the resultant force. So let's see if there is any option. There is no option, I guess. Yes. So the answer is 127.02 kilonewton per meter. So like this you can do the question number 10. So let's see the question number 11, which is a triangular gate base 2 meter, height 1.5 meter, lies in a vertical plane. The top vertex is 1.5 meter below the surface of a tank which contains oil of a specific gravity 0.8. Considering density of water and acceleration due to gravity to be 1000 kg per meter cube and 9.81 meter per second square respectively, the hydrostatic force in kilonewton exerted by oil on the gate is. So here in this question we have given a triangular gate. So there is, let's see, there is a triangular gate which is having base of 2 meter and height as 1.5 meter. Okay, and it is lying on a vertical plane. The top vertex is 1 meter below. So in the top there is vertex that is 1.5 meter below the surface of tank. That means if I say this is in vertical plane, so I am seeing the side view, right? So this is the vertical plane of the triangle which is already 1.5 meter, and then it is also below 1.5 meter of the free surface. And they are asking me everything is given. They have given a liquid or oil which is having specific gravity, specific density as 0.8. Okay, in respect of water. So we have to calculate the hydrostatic force. Because the body is vertical, there is only, yani that means it is a planar body, so there is horizontal force acting. That force is having a formula we have already seen, rho g h bar into area. Area is projected area. So if we are seeing the projected area, it is a triangle. This is the projected area of this particular plane. So the hydrostatic force is acting on this particular area everywhere. If you try to imagine. So if I put the density is 0.8 into 1000, which is of water. So it is 800 into acceleration due to gravity they are asking to take as 9.81. So I will take 9.81, and h bar, the height of the CG of the body. CG of the body will be somewhere here. Okay, that CG is 2/3 of the total height, right? So 2 by 3 of total height is 1.5 meter. So 1.5 2/3 will be nothing but 1 meter. So it is 1 meter of the triangle, and from the free surface is the height. So from the free surface is 1.5 plus 1 cg, right? Plus 1, that is 1 meter. So I am having total height as 1 plus 1.5, that is 2.5. 2.5 into area. So area will be 1 by 2 into 2 meter is the base and height is 1.5 meter. So total, if I calculate, I get 29430 Newton is the force value. I want it in kilonewton, right? So the answer I want in kilonewton, I will divide by 1000. I am getting force as 29.43 kilonewton. So this is the answer I am going to put, 29.43 kilonewton. So this is question 11th. So let's see question number 12th, which is 3 rigid buckets are of identical height and base area. Further, assume that each of these buckets have negligible mass and are full of water. Negligible mass, full of water. The weight of the water in these buckets are denoted by W1, W2 and W3 respectively. So the weights are denoted by W1, W2, W3. Also, let the force of the water on the base of the bucket. The force of the water on the base of the bucket is F1, F2 and F3. Which of the following options are correct? See, they have given the relation between weights and force. They are saying that these are having same base area. So the base area is same for all buckets. Let's say it is A, this is as also A and this is also A. So the base area is same in this picture. So we can see, if I make, that means they are saying the base is same. So base is this much, this much, this much. So here the bases are same. One is something like this. Another one is something like this. And next is something like this, right? So bases are same, and they are saying, and it is full of water. All 3 buckets are full of water. So if the first bucket has this much water, second will be, if I compare it with first will be somewhat like this. There we are having more water than first bucket. In the third bucket, see, if we compare it with first bucket, it will be somewhat like this. So here the water is less than the first bucket. So if the first bucket is having W1 weight, obviously the volume is more, weight will be more in the second bucket. So second bucket will be having more weight than first, and then third bucket is having less weight than first. So I have, do we have any option like this? Yes, we have the option here, W2, W1, W3, and W2 is greater than W1 is greater than W3 is also there. We are having two options. Now I have to choose one according to the force relationship. So see, force is nothing but hydrostatic force at the bottom. Hydrostatic force is rho g h, right? And h depends on, so the force depends on the height of the body. Height is same, identical. They have given h, h, h. So the force and rho is same because water is there. G will always be same on the earth. So it is, height is same. So we can say F1 is equal to F2 is equal to F3. So we are left with option number 3, option number D, and B is correct. B is incorrect and option number D is correct. So the answer, final answer is option D. So here we complete the questions of all the previous year question of chapter number 3, which was hydrostatic forces, buoyancy. So let's meet in the next chapter. Thank you.